Hello, in this video we're going to look a little bit more at acidity of aqueous solutions and how we quantify that and how we go back and forth between different ways of quantifying acidity, and then we'll look at its effect on water. All right, so we'll kind of relate concentrations of H plus and OH minus and pH, and then talk about how rainwater is acidic and how what can cause the pH of the ocean to become low and the ocean to become more acidic. All right, so what is pH? So this is a way of quantifying or measuring the concentration of H plus ions that are present in solution. And it's a log-based scale, which is a little bit more convenient because it brings the numbers down to something. It's easier to talk about 7 than it is to talk about 1 times 10 to the negative 7th power. So that's why we have the pH scale. And so pH equals the negative log of the concentration of H plus ions. And this is base 10 log. And so as an example, if the concentration of H plus ions was 1 times 10 to the negative 3rd moles per liter, or molar, then the pH, we could plug that into this formula, and the pH would be 3. Okay? And so one thing to keep in mind is if the pH is changing by 1 unit, that represents a change in 10 times the concentration of H plus. Okay, so if the pH increases from, say, 3 to 4, then the concentration of H plus ions is a factor of 10 higher. Okay, so that's a big change. And here's another example of that. Okay. So when kind of doing calculations with the concentration of H plus and OH minus, and it's useful to use this relationship involving the ion product constant for water, and that's K sub W. Okay, and that equals the concentration of H plus ions times the concentration of OH minus ions, and that equals 1 times 10 to the negative 14th. Okay, so what this means, that means if we either know the concentration of H plus ions or the concentration of OH minus ions or the pH, we can calculate, if we know any one of those three, we can calculate the other two. Okay, so in a neutral solution, the pH equals 7, and the concentration of H plus ions equals the concentration of OH minus ions, and that equals 10 to the minus 7th. If you have an acidic solution, pH is less than 7, and the concentration of H plus ions is greater than the concentration of OH minus ions. And in a basic solution, the pH is greater than 7, and the concentration of OH minus ions is larger than the concentration of H plus ions. Okay. This is another way to kind of look at it, which I think might be helpful because it's like a visual representation of these scales. So on the top here, we've got the concentration of H plus ions, and you can see that's powers of 10. Here we've got the pH, so that you can kind of relate these to each other. Again, the negative log of the concentration of the H plus ions equals pH. So if we were to take the negative log of 10 to the negative 6th power, that would equal 6. Okay, and you can see acidic solutions are those that have a pH less than 7, and basic solutions are those that have a pH greater than 7. We can also relate this to common solutions that you might be familiar with. So for instance, Coca-Cola or Dr. Pepper, any sort of colas, they're going to have a pH of less than 3. Whereas milk of magnesia would have a pH between 10 and 11. You can see seawater is slightly basic, milk is a little bit acidic, and stomach acid is fairly acidic. Okay. All right. So it turns out, if we go back here, here's normal rain, okay, has a pH between 5 and 6, so it's slightly acidic. So why is that? And that has to do with carbon dioxide. So one component of the atmosphere is carbon dioxide, and this will dissolve slightly in water, and that's going to react to produce carbonic acid in an acidic solution. So CO2 plus water will go to form carbonic acid. And then this can dissociate slightly, leading to the formation of H plus ions. And remember, the more H plus ions you have, or the higher the concentration of H plus ions, the lower the pH and the more acidic the solution is. Okay, and that gives us a pH of 5.3. So this has important implications for rain and for ocean acidity, and also the acidity of lakes and streams. And so we're going to look at ocean acidity a little bit in the next couple slides. Okay, so rainwater is naturally acidic, but the ocean is basic naturally. And there is some species that are responsible for maintaining ocean pH. So we have the carbonate ion, CO3 2-, we have the bicarbonate ion, HCO3-, and then carbonic acid, H2CO3. Okay, and these are all in relationship with each other based on chemical equations and chemical equilibria. So we're going to kind of look on this slide at some of those. Over the past couple centuries, the amount of carbon dioxide in the atmosphere has increased, and so that's dissolving in the ocean, and that forms carbonic acid. Okay, and that leads to ocean acidification. Okay, so what's going on here is CO2 is in equilibrium between the atmosphere and the ocean. As we increase the amount of CO2 in the atmosphere, that's going to increase the amount of CO2 that dissolves in the ocean. That reacts with the ocean water to form carbonic acid, which then dissociates to form H plus ions and HCO3- ions. So as we increase H plus, the concentration of H plus in the ocean, that makes it more acidic, have a lower pH. Okay, and the reason that's significant is it can react with carbonate present in the ocean to form bicarbonate. All right, so the reason we care about this carbonate is if we are using up the carbonate to react with the excess H plus ions, well, that carbonate comes from calcium carbonate. And there's some sea creatures like coral that are made of calcium carbonate. Okay, so kind of the net effect is if we increase the amount, ultimately, if we increase the amount of CO2 in the atmosphere, this increases ocean CO2, which leads to a higher concentration of H+, which leads to a lower concentration of CO3 2- or carbonate in the water, which leads to coral reefs dissolving. That's kind of the big picture and the details, I guess. So that's one reason why we might be concerned about ocean acidification. Okay, now we can also talk about lakes and streams and how acidifying lakes and streams can affect animals and aquatic life. So normal aquatic life likes to live in this pH between maybe 6.5 and 9.5. As we make our lakes and streams more acidic, fish become unhappy they start to disappear. And then if you get too acidic, most aquatic life disappears. And then we say lakes are dead once you get to a pH of 4. Okay. Now, we're really fortunate in the Midwest, kind of the Great Lakes region, in that we have a lot of calcium carbonate in some of our surface geology. And so that helps to kind of buffer the effect of the acidic rain. And so we don't have as much lake acidification as maybe a place like New York. So that's going to conclude this video. Thanks for watching.